Okay, there was an error actually, so I was recording, but then something happened and it broke, so starting from the beginning again. Today, we'll be talking about variational quantum eigensolver optimization, specifically a recent paper that introduced an algorithm called Rotosolve. And so first, just as a reminder, the density matrix P, or rho really, is given for pure and mixed states as the following: the sum of this outer product here, and this term pi is only present in mixed states. And so we can see that if we take the expectation value of an operator A, we can write it as a sum of discretes, and then we just add this temporary variable in here I, rearrange it, and because we know the trace of a matrix is equivalent to, I should add an I right here, it's equivalent to this term over here, we can rewrite the expectation value as a trace of the density operator and the density matrix and the operator. So this was just a review. If you didn't know that the expectation value of an operator can be expressed via trace of density matrix, but like if you did know that, then that's all you needed to know from this thing. So we start off with a Hamiltonian H parametrized by theta, and we know that these unitary parametrized rotation gates can be expressed in the form cosine theta over 2 identity minus I sine theta over 2 times g, where g is the generator, which is a linear sum of Pauli terms. So then we can express this, as shown before, as a trace of the density matrix rho, or I think it's rho, maybe it's P. I'm just going to call it P from now on. I know that it's a Greek letter. And H, which is the Hamiltonian operator, and then these are the circuit gates that are being applied, not necessarily all parametrized. Here we just drop the notation and refer to a single gate. We plug in this term above for this parametrized gate. You can see this is just straight plugging in, and now we just distribute the H term and the P term to get this. Then we have this term. This is just me rewriting it. And remember that H, G, and P are all matrices or operators. And so I guess, every operator is a matrix in that form. And so keep in mind that order does matter in these cases. So PG is not necessarily the same as GP. So now we can expand it out. So we do this term times this term, and we get HP cosine squared. And note, I just dropped a theta over 2. They're still there. I just didn't feel like writing them every time. Expand this term out. We get I sine cosine HPG. Expand. That was that term. Now we do this one. We do negative I sine cosine. This time it's HGP. And expand this last one out. The i's cancel. And so this becomes sine squared mgpg. So keep that in mind. That's going to be important. So here you might think these terms cancel out, but keep in mind these are not necessarily the same. And so if you remember from any quantum mechanics class, the commutation relation of an operator is, so you might see, okay, well, this is obviously PG, GP minus, so this is a commutation relationship, so we can express it compactly. We just do HP cosine squared plus I sine cosine H P comma G. And then we do plus sine squared MG. And now we can see, okay, the trace, these constants, these are all constants that we can pull out of the trace, and the trace is, you can apply it linearly, so we can rewrite this as, so we pull out this cosine squared. I'll reintroduce the parameters here. They were always there, and now we have the trace of that, and now I pulled out the I'm just pulling out constants because you can imagine, these are just applied to every element in a matrix and therefore don't need to be inside the trace, but every matrix element or every matrix whole unit does. And so then we have this whole big term. And I ran out of room. And so that's the whole term. And so that's pretty complex, doesn't look terribly useful, but as we'll see in a second, this is actually pretty useful. So first, we can consolidate this middle term. And we can see if we rewrite this format as, I'm not going to actually do all of the derivation of this middle term, but we can see if I have this, let's suppose theta is pi over 2 here, and theta is negative pi over 2 here. We know this is the same trace operators as above. We have the h, then we have the u, this is theta over 2. Density matrix U complex conjugate theta over 2. And then we have the same thing for the negative pi over 2. And from there we can rewrite this as cosine and sine. But remember, cosine of pi over 2 is 0. And sine of pi over 2 is 1. And so from there, we can just rewrite this. This is a pretty simple derivation. If you want to do it out yourself, we can rewrite this as h gp. From there we have plus I trace hpg. And so we can see this is the commutation relationship as detailed above. So that's just a little side note. So now we can replace that term above with the new expectation value calculations. So we can do cosine. I'm once again dropping the parameters. But before we do this, let me just say one more thing. We know that the expectation value of the unparametrized Hamiltonian is just IE. This is just the, so this is just trace of HP. And so that's an easy note. And the second note is that if we have h of pi, remember that this is just the negative expansion. So if we have, we don't have to do the whole expansion out, but if we have this negative pi over 2, because remember it's theta over 2 in these terms, we can expand this out, and so we do cosine over 2, do this whole thing. And so if you remember, cosine of pi over 2 is 0, and so we're left with just doing the whole trace operation again. I'm not going to write this whole thing out. We have trace of h GPG. Those are just pretty straightforward if you just look at the nature of the plugging in these terms, these pi and 0 into the sine equation as before. You can see it's like a two-step process to derive them. And so with all of these terms, we can note, well, I do want to say, I think I misspoke when I said These pi over 2 terms don't cancel because this is actually pi over 4, but they do just make the derivation pretty easy because it's pi over 2 parametrized is actually pi over 2 divided by 2, which is pi over 4. So we have this whole expression here as cosine squared, and then we know h0, we have plus sine, cosine, then we have pi over 2 minus pi over negative pi over 2. And last but not least, we have the plus sine squared. You notice I keep writing m. That's just because that's the term they use in the paper rather than h. And so I keep accidentally writing it because I am looking at the paper simultaneously. And so there we go. So this is the better expression. You might see where we're going to go about optimizing it because we just changed it from a nasty looking equation to all things that can be sampled from the circuit. We can estimate each of these operators or each of these expectation values of the operator. And so we can rewrite this into the form a sine theta plus b plus c, just reformatting it for ease of minimization. And so we can see in this case that there's a fancy identity, a cosine of x plus b sine of x equals the square root of a squared plus b squared times sine of x plus arctan of a over b. So that's a nasty sort of expression algebraically to work with. So I'm just going to sort of tell you the answer here, that b is equal to arctangent of 0 minus h pi divided by h pi over 2 minus h negative pi over 2. So the reason I'm only showing b is because if we look at this, we can see oh, and also c, I should specify. C. A doesn't really matter for reasons that I'll explain in a second. A is just 0 plus pi. This is just derived from that trig identity I said earlier, just a lot of algebra that doesn't really matter to do. And so we can see from this equation, we can see, okay, a is just a constant. In terms of parameters, where's the minimum going to be? So we want c to be as small as possible. We want a to be negative and as big as possible. But really, what matters is we want theta plus b. I should write this on a new slide. So if we want to minimize this term, we want theta plus b to equal negative pi over 2. Or this is equivalent to 3 pi over 2. Because this is sine of that will equal -1. And so that will be as small as possible, the term. The term will be as small as possible. And so now we can say, okay, well, from here we could just solve, we have all these terms. We could do the expectation value for each of these 4 different terms. And just get this easily, but we can actually reduce this to 3 samplings, which makes it a lot more efficient. If we remember that any of this, if we have some parameter, we do plus or minus, we can see that this, we do plus, this equals a sine of theta plus pi over 2 plus b plus c in this format. And so then we can see, okay, if we do minus, we can see that theta minus pi over 2 equals a negative a. This is just basic trig identities. Theta minus pi over 2 plus b plus c. And so we can see that, that the expectation value plus is equal to the negative expectation value of theta minus. Because, I mean, this makes sense. It's exactly what we would expect, knowing the knowing the nature of the periodicity of sine and trigonometric functions. And so now that's just a note that will make it easier to sample and do less parameters, or less sampling of the parameters. We can see that, okay, if we want to solve for b, to minimize b, we can see, okay, we have theta equals, from above up here, we see theta equals, at the minimum, negative pi over 2 minus b. And so this is minimum, which is, you know, what we want, because we want theta to equal negative pi over 2. That way it will, the sign of that function will be at a minimum. And so we can write this out, and we can see that this function, if we're solving for b, and we want to utilize this terminology, you know, normally this requires 4 sampling, 0, pi over 2, and negative pi over 2. If we want to utilize this new format, which we can say, you know, we can write this new c in the form 1/2 h over 2 minus h negative pi over 2. If we want to utilize this new format to minimize the number of calls we make to the circuit, then we can write in the format, we're using a new variable here because this is just converting b basically into the format of this 3 samplings required. So we know that this is sine of plus b, and this is sine of, and this is just, you know, definition of tangent and the periodicity. And so we can immediately look up here and be like, hey, these were just the terms we were using up here, and we can see that this, you know, if we know that c is equal to 1/2 the expectation at plus pi over 2 plus the expectation at negative pi over 2, we can write this as and then over okay, now if we just subtract the c from these terms, we will get towards our final answer, which is, we can see that this, I should specify this tangent of b equals now, so c, remember, is 1/2 of that. I should just go back. This is c, remember, this term right here that we've rewritten. And so we can see that applying this out and taking the 1/2 out of both terms, first of all, we can see that this is, so that's the first term of the above. We can see we have this first term up here. We're subtracting c. So we have h theta plus pi over 2 minus h minus pi over 2. And so now we can see that this whole thing can be expressed using just 3 circuit evaluations instead of the original 4. That's what this whole thing was for. Really, we could go back and go back here and from this stuff optimize it. But this whole work was trying to save 1 circuit evaluation, which is, you know, in the end, if you're doing this many, many times, it adds up. And so now we can see solving for b, you just arctan this and then subtract phi, and so we have b equals arctan of this minus that. And so if we want the minimum value, remember that the minimum, it was negative pi over 2 minus b, which is equal to negative pi over 2 minus this arctan term plus b. So this big term goes in here, which I'm not going to rewrite. So now we can see, okay, if we know what this optimal theta should be, we can now understand the algorithm. So we have this term, we have this expression for the optimal value of theta. And so from here, we can say, okay, well, how do we choose phi? We can choose this just randomly. There's heuristics to choose it. But I'm going to call this equation 1. I'll refer to this as. So we can repeatedly, this is now the algorithm, which we just did all of this derivation for. So if we have parameters theta, a list of parameters, we can select a random phi. We can fix all angles except that one. We can just do and then we can get sample these 3 terms. And then we can use I guess I didn't really need to write this part. That just might confuse it. And then we can set this equal via equation 1. And then we can just stop. So this is really simple, right? We have this equation here. We sample 3 times. We update. We do this optimization loop. This whole thing, all of this algebra was just to derive this optimization. All of this was just to derive this loop right here in this single equation, which I will box. Note that this term is here. So if we go and we look at the code for this, we can see all of that work was done in just 15 lines of code. So we have Rotosolve. So we have this function which generates the estimation of the expectation value of the operator. We have a number of parameters and we have a number of iterations. So we initialize the theta. We go through for every iteration. We create a random phi. I just do this to sort of temporary information. I guess this isn't entirely necessary. I just do it for clarity, I guess. Then we say, okay, we set it equal to phi, keeping all the other parameters constant. We get an estimation of the expectation value. We add pi over 2. We repeat that. We subtract pi over 2. We repeat the estimation. Now we just set it equal to the original term minus pi over 2 minus this arctan. It's just arctan 2. This is really division. And then we return the final estimate and the final parameters. And so this is really simple, exactly as outlined in the explanation. So if we go through and go back to the last VQE we did, minimizing the hydrogen atom, we have Nelder-Mead, we have simultaneous perturbation of, I don't remember what SPSA is, but it's a common one for stochastic optimization and noisy optimization. And then we have Rotosolve. And so, so if we run these many times, we can get, I'm just doing the same optimization loop for each of them many times, and then I will show the results. This takes a decent amount of time to run, and so I don't want to. Let me bring up the image, and then let me. So let's add a window capture. Oh, 1 second. Okay, here we go. So we can see this is the same graph I showed yesterday. Here's the Nelder-Mead optimization, and that's one standard deviation, that shaded area. Do I have to zoom out? There we go. So this is the SPSA. You can see that there's the way it works. It's very confident. Here's the roto. And so when we compare all of them, we can see that, let me zoom in. You can see roto is this orangish one. You can see roto seems to be the smoothest of all of them. This is we can also look, that's pretty noisy. SPSA, you can see, is kind of jagged at the end. Roto is nice and smooth. And so, I mean, that looks like a nice curve right there. And so this is a single parameter. I didn't have the ability, I guess, to do more complex ones. I'm still trying to look for more information on how to do, like, a lithium hydride is a common VQE. But I found, like, the parameters, but I can't find if there's, necessary operations for transforming all these large qubit systems into readout operators. Specifically, if you remember with VQE, we have to apply certain gates at the end for the unitary transforms to Pauli readouts or Pauli measurements. I don't know, I was looking, but I haven't found any success looking for how to do that for larger systems. But yes, this is just the Rotosolve algorithm as presented in the recent Quantum Journal paper. And so once again, the code will be available. The paper will also, I will also have linked, and hopefully that made some sense. I know it was pretty long-winded getting there. I'm doing lots and lots of algebra, but we can see a technique of optimization that requires only 3 samples per parameter.